This example is based on a very famous machinery that was built by Watt, and it's called Watt's governor or Watt governor. Please search that in the internet to get more insight on it. So this is called the Watt governor. What it is used for is it's a control system basically, and it governs the speed of rotation in a steam engine. It was used in that era of the steam engines, and the inventor was Watt. That's why it's called Watt governor. And this problem is about the fundamentals of its working principle. Now, again, we will have some assumptions here. Otherwise, we need to talk about the concept of rigid body systems. To just get rid of that, we can just assume that what happens here is that these two particles are rotating about a beam here, and then these connecting beams have negligible inertial properties, negligible mass. Otherwise, we need to again consider these as rigid bodies. But now we can just consider these two particles as they rotate about this axis. Now, as they are rotating with 40 revolutions per minute or 40 RPM, we can find the equivalence of that in terms of radians per second. Since we are working with SI units, we need to do it in radians per second. That means you need to multiply this 40 by 2 pi. Each revolution is 2 pi amount of radians. So 40 times 2 pi. And then in each second, how many rotations we're going to find out. So you need to divide that by 60. Okay? And that would give us the result in radians per second. Whatever it is, I think it's written out over here. So it's 4.19 radians per second. Anyways, going back to this question. Now, in order for these to rotate and not fall down, there's a force acting on here, and which is pushing this collar up. And the reason that these particles would fall is because of the gravitational force, obviously. There's the gravitational force or gravitational acceleration acting in this direction, and mass times gravitational acceleration will give us the force acting on the particles, which will make these particles fall. But as we have this force, it maintains its current location in terms of the height, and then makes a rotation with some omega speed. Now, at this instant of 40 revolutions per minute, this theta angle right over here is 90 degrees. So this is the 90 degrees angle. And the F force is then changed, increased, so that this theta moves from 90 degrees to 60 degrees. Why the force should increase? If you redraw this, if you try to redraw this for 60 degrees, this is at a fixed location, so we need to draw it from here. That means it will be around someplace here. This for 60 degrees, it's going to look something like this. So this is the connection port here. And, oops, okay. And this is about 60 degrees. So what has happened is that this ball has moved up. Just try to draw the location of the ball. Has moved up. There's our ball. Okay. It has moved up. So in terms of the gravitational potential energy, it has gained some potential energy, and on top of that, it has moved to the side. Now, only in terms of the gravitational potential energy, if the gravitational potential energy is increased, that means there should be an work done by some external force, by another force, or the potential energy, the kinetic energy will be transferred to the potential energy. So in order to understand that, we need to take a look at what happens to the kinetic energy. And in order to understand the kinetic energy, we need to understand what happens to the speed of these particles. So let's investigate it in terms of the speed of the particles. The information we have is the rotational speed omega. With respect to this omega and the, let me just try to go here, the distance up to the particle, so this distance, let's call it d, times omega, will be the velocity of this particle. Okay? And the velocity of the other particle will be in a similar manner, since two parts of this mechanism is the same length. In that sense, there will be a total angular momentum of this system of two particles, and it will be composed of, if you consider m as the mass of the particles, m omega d is the velocity, times d, and we can show it by the square, is the angular momentum. 2 times of that would be the total angular momentum. Now, if this force amount has changed, the question is, would it affect the angular momentum, or will the angular momentum stay the same? The angular momentum's direction is vertically upward with respect to the right-hand rule. If the omega is in this direction, the velocity of this particle on the right is inside the page, the velocity of the particle on the left is outside the page, and the angular momentum direction is in the upward direction in that sense. The axis defining the angular momentum direction is in the upward direction. Now there should be a moment in that direction. Now what would cause that moment? F is already in that direction. There's no moment arm, so the change in F would not affect that moment. How about the moment by the gravitational acceleration? They will generate a moment because of the force, mg force in these directions, right? There's an mg force in this direction. But then the moment of this mg direction force will not be in the vertical direction. Okay, so that means the angular momentum will be conserved. There is no angular impulse applied to this system as it is moved from 90 degrees to 60 degrees. So the angular momentum of the particles, the total angular momentum of the particles in the second system should be equal to 2 times m times w omega, 2m omega d squared. But what has changed is the d here. D has become a little bit larger as it is moved up, and we can calculate that, and we can call that d prime, and we can say that this is equal to 2 times m. Now there is a new omega, so let's call it omega prime d prime squared. So based on these trigonometric equalities, we can calculate this d prime, and omega is known, d is known, the only unknown is omega prime, so we can find the angular speed of the particles at that instant. If we know the angular speeds of the particles at that instant, then we can calculate the kinetic energy at that instant as m omega prime d prime squared. Right? That would be the kinetic energy of each particle at the instant. So the difference between the kinetic energy from the first instant to the second instant, and because of the gain of the potential energy, these all are a result of the work done by F, and that is asked in the question. Determine the work done by F in changing the configuration. What will change as we change the configuration? Potential energy will change, and also the kinetic energy will change. That's what we found out in the first part of the problem, because the omega prime has changed. So the next set of equations are working on this. The first part is that the angular momentum will stay the same because there's no moment about or applied as a result of the change of the f. And we are able to calculate the new omega prime or omega 2 here as 3 radians per second. So it has dropped from 4.19 to 3 seconds, and the main reason for that is R2 is larger than R1. So these particles are more away from the center of rotation, and as a result of that, the moment arm is larger, the speed will be smaller for the same amount of angular momentum. So the speed drops down. Now, in order to calculate the work done by this force, we write out this equation of work results in the change in the kinetic energy and the change in the potential energy. There is no spring system here, so the delta VE is not written over here. And the total work done is based on the change in the kinetic energy, the second instance minus the first instant kinetic energy, and then the change in the potential energy. And why the potential energy changes? Because these particles move up as this theta is moved from 90 degrees to 60 degrees as a result of this F force. And we find out the work done by this F force is about 5 joules for this action.